When measuring recent geological history, the natural starting point is to look at large physical processes, like the slow carving of a deep river gorge. But macroscopic erosion rates are highly unpredictable. The Niagara Escarpment retreats at roughly 1 foot per year today, but historical water volumes and rock density fluctuate over centuries, making erosion a poor metronome for precise timekeeping. To achieve absolute chronological accuracy, we must abandon macroscopic erosion entirely and look to microscopic accretion. Specifically, we look for a meromictic lake. This is a rare hydrological environment where the water column is permanently stratified. The deep, dense bottom waters never mix with the oxygenated layers at the surface. Because this isolated bottom layer, the monomolybdean, is heavily alkaline and anoxic, it prevents infaunal invertebrates from surviving. Without bioturbation, the sediment deposited on the lakebed remains completely undisturbed. In this perfectly preserved environment, seasonal deposits settle into distinct, alternating mineral layers known as varves. Every calendar year prints a distinct couplet of these layers, forming an absolute geological clock. By extracting the core and measuring the millimeter-scale thickness of these individual layers, the physical mud is translated directly into a continuous, one-dimensional data waveform. Treating this sediment as a numerical array allows geoscientists to apply advanced signal processing to the geological record. Extracting the specific frequency domains from these mud layers allows us to isolate the massive global climate phenomena that dictated their deposition. Analyzing these strata as data arrays allows geoscientists to assign precise calendar years to the shifts that define the start of the Anthropocene. The formation of these varves relies on an exact chemical threshold occurring in the lake's upper layer, the mixolydian, during the summer months. The required triggers are strict. The surface water temperature must exceed 15 degrees Celsius, and the water's pH must rise above 7.76. This dual-axis line graph demonstrates the result. Crossing these thresholds triggers the precipitation of authigenic calcite crystals, sinking to form a light mineral layer. When winter arrives, thermal collapse causes a plankton die-off, sending a thick, dark layer of organic matter to the lake floor. This binary seasonal process physically prints a distinct light and dark varve couplet for every single calendar year. The exact thickness of the calcite layer in the summer, or the organic layer in the winter, correlates strictly to the intensity of regional climate factors during those months. Driven by this biogeochemical mechanism, the lakebed operates as a high-fidelity recording instrument, perfectly calibrated to log its surrounding environment. Retrieving the most recent decades of this record presents a severe physical obstacle. Dropping a standard gravity core into the lake captures deep historical layers, but it destroys the loose, uncompacted sediment at the top. As the core is pulled up through the water column into lower atmospheric pressure, interstitial gases trapped in the mud rapidly expand. This outgassing blows out the delicate sediment-water interface. To solve this, researchers use a freeze core, a hollow aluminum wedge injected with a circulating slurry of dry ice and ethanol. Lowering this supercooled device into the sediment cryo-locks the layers directly to the metal face before any gas escapes. Because the water within the sediment freezes solid before the trapped gases can expand, this method completely bypasses mechanical compaction or mixing. Overcoming this extraction hurdle is the only reliable way geoscientists can secure a flawless physical record of the exact transition into the modern era. To make the relative varve counts mathematically useful, they must be anchored to absolute historical timestamps. The first major calibration point relies on the extreme climatic conditions of the 1935 Dust Bowl. During that turbulent decade, severe, intense drought and extreme temperature anomalies caused a massive atmospheric dust transport across North America. In the lake, the extreme heat of 1935 forced the precipitation of an anomalously thick, bright calcite layer, locking that calendar year into the core. The second crucial anchor stems from the search for the global boundaries stratotype section and point, the physical marker for the Anthropocene epoch, targeting 1950. The mid-20th century era was defined by global thermonuclear weapons testing, which dispersed radioactive isotopes high into the upper atmosphere. As this radioactive fallout settled down, a massive, sudden spike in total plutonium permanently altered the stratigraphy of the lakebed. By cross-referencing this plutonium spike with the known isotopic decay rates of cesium-137 and lead-210 within the sediment, researchers can verify the exact 1950 boundary. Aligning millimeter-scale physical ARV measurements with absolute isotopic fallout provides the unassailable chronological anchor required by the Subcommission on Quaternary Stratigraphy. With the timeline secured, measuring the exact thickness of every VARV from 1870 to 2000 produces a continuous annual data array. To find repeating patterns, researchers apply Thomson's multi-taper method, a baseline spectral analysis technique used to identify dominant frequencies within the data. A Fourier transform decomposes a raw, noisy waveform, separating it into a static bar chart of isolated sine wave frequencies. But this reveals the stationarity problem. The chart proves what frequencies exist, but provides zero data on when those cycles started, stopped, or changed. Planetary climate teleconnections are inherently complex, non-stationary systems. They pulse, fade, and interact unpredictably over the span of decades. Resolving this timeline requires a computational upgrade, continuous wavelet transforms, or CWT. Rather than collapsing the data into a static list, CWT maps time-varying periodicity. It tracks the historical timeline of when specific climate frequencies strengthened or weakened. Moving from a static frequency domain to a detailed time-varying model is essential to decode the chaotic, overlapping rhythms of a living planetary climate system. This continuous wavelet transform heat map is generated directly from the lake's VARV thickness data. The parabolic line delineates the cone of influence, separating the valid data from mathematical edge effects. Inside the valid data, a distinct high-frequency cycle emerges between 2.1 and 2.4 years. This band aligns with the quasi-biennial oscillation. Shifting stratospheric winds alter spring ice melt over the lake, recording a distinct 2-year pulse. Further down the y-axis, a broader, irregular frequency band appears between 2 and 7 years, becoming highly prominent after the 1950s. This traces the El Niño Southern Oscillation, linking global temperature anomalies to the region's localized winter precipitation. Deep in the dark organic layers, an 11-year cycle is also visible. This correlates to the Schwabe sunspot cycle, whose slight variations in solar output are amplified by changes in atmospheric ozone production. The raw physical thickness of the mud is dictated entirely by the complex, overlapping interference of these massive planetary-scale cycles. A structural anomaly in the VARV data from the mid-1970s illustrates the concept of phase interference. This animated timeline highlights the 1976 Pacific Decadal Oscillation Great Regime Shift, a moment when the Pacific Ocean transitioned from a dominantly cool phase to a warm phase. That single decadal shift physically suppressed or amplified the expression of the other, shorter-term climate signals in the lakebed for years afterward. Integrating limnology, cryoengineering, and signal processing reconstructs exactly how planetary climate systems interacted